မင်္ဂလာပါ။ဒီနေ့က LS တွေဒီ linear combination ထိပြီးသွားတယ်ပေါ့နော်။ဒီနေ့အဲ့ဒါနဲ့အခုလောဆယ် LS ကဒီ dependent linear တစ်ခုနဲ့တစ်ခု dependent ဖြစ်တဲ့ဟာရဲ့ independent ဖြစ်တဲ့ဟာလေ့လာကြမယ်ပေါ့နော်။ဒီဟာလေးလည်းဆို machine learning course မှာပြောထားတယ်ပေါ့နော်။ဒီဟာလေးပို့ပြီးတော့နားလည်အောင်ကြည့်ကြမယ်လို့နော်။ Okay အဲ့ဒါဆိုရင်ထုံးစံအတိုင်းပဲ LS ကို unmute လုပ်လိုက်ရအောင်ကြည့်လို့ပေါ့နော်။
Let's say I had the vectors. Say I had the set of vectors. That big. Let's say one of the vectors is the vector 2, 3, and then the other vector is the vector 4, 6. And I just want to answer the question, what is the span of these vectors? And let's assume that these are position vectors. What are all of the vectors that these two vectors can represent? Well, if you just look at it, and remember, the span is just all of the vectors that can be represented by linear combinations of these. So it's the set of all the vectors, and if I have some constant times 2 times that vector, plus some other constant times this vector, it's all the possibilities that I can represent when I just put a bunch of different real numbers for C1 and C2. Now, the first thing you might realize is that, look, this vector 2, this is just the same thing as 2 times the vector as the 2 times this vector. So I could just rewrite it like this. I could just rewrite it as C1 times the vector 2, 3 plus C2 times the vector. And here I'm going to write, instead of writing the vector 4, 6, I'm going to write 2 times the vector 2, 3. Because this vector is just a multiple of that vector. So I could write C2 times 2 times 2, 3. I think you see that this is equivalent to the 4, 6. 2 times 2 is 4, 2 times 3 is 6. Well, then we can simplify this a little bit. We can rewrite this as just C1 plus 2C2, all of that times 2, 3 times our vector 2, 3. And this is just some arbitrary constant. It's some arbitrary constant plus 2 times some other arbitrary constant. So we could just call this C3 times my vector 2, 3. So in this situation, even though we started with 2 vectors, and I said, well, you know, the span of these 2 vectors is equal to all of the vectors that can be constructed with some linear combination of these, any linear combination of these, if I just use this substitution right here, can be reduced to just a scalar multiple of my first vector. I could have gone the other way around. I could have substituted this vector as being 1/2 times this and just made any combination a scalar multiple of the second vector. But the fact is that instead of talking about linear combinations of 2 vectors, I can reduce this to just a scalar combination of 1 vector. And we've seen in R2 a scalar combination of 1 vector, especially if they're position vectors. For example, this vector 2, 3, it's 2, 3, it looks like this. All the scalar combinations of that vector are just going to lie along this line. So 2, 3, it's going to be right there. They're all just going to lie along that line right there. So along this line, going in both directions forever. And if I take the negative values of 2, 3, I'm going to go down here. If I take positive values, I'm going to go here. If I get really large positive values, I'm going to go up here. But I can just represent the vectors, and when you put them in standard form, their arrows essentially would trace out this line. So you could say that the span of my set of vectors, put it over here, the span of the vectors, let me do it this way, the span of the set of vectors 2, 3, and 4, 6 is just this line here. Even though we have 2 vectors, they're essentially collinear. They're multiples of each other. I mean, 4, 6 is, if this is 2, 3, 4, 6 is just this right here. 4, 6. It's just that longer one right there. They're collinear. These 2 things are collinear. Now, so in this case, when we have 2 collinear vectors in R2, they essentially, their span just reduces to that line. You can't represent some vector like, you can't represent, let me do a new color. You can't represent this vector right there with some combination of those 2 vectors. There's no way to kind of break out of this line. So there's no way that you can represent everything in R2. So the span is just that line there. Now, a related idea to this, notice you get two vectors, but it kind of reduced to one vector when you took its linear combinations. The related idea here is that we call this set, we call it linearly dependent. Let me write that down. Linearly dependent. This is a linearly dependent set. And linearly dependent just means that one of the vectors in the set can be represented by some combination of the other vectors in the set. And a way to think about it is whichever vector you pick that can be represented by the others, it's not adding any new directionality or any new information, right? In this case, we already had a vector that went in this direction, and when you throw this 4, 6 on there, you're going in the same direction, just scaled up. So it's not adding us, it's not giving us any new dimension, letting us break out of this line, right? And you can imagine in 3 space, if you have one vector that looks like this, and another vector that looks like this, two vectors that aren't collinear, they're going to define a kind of a two-dimensional space. They can define a two-dimensional space. Let's say that this is the plane defined by those two vectors. In order to define R3, a third vector in that set can't be coplanar with those two. Right? If this third vector is coplanar with these, it's not adding any more directionality. So this set of 3 vectors will also be linearly dependent. And another way to think about it is that these 2 purple vectors span this plane, span the plane that they define essentially. Right? Anything in this plane going in any direction can be any vector in this plane. When we say span it, that means that any vector can be represented by a linear combination of this vector and this vector, which means that if this vector is on that plane, it can be represented as linear combination of that vector and that vector. So this green vector I added isn't going to add anything to the span of our set of vectors. And that's because this is a linearly dependent set. This one can be represented by a sum of that one and that one, because this one and this one span this plane. In order for the span of these 3 vectors to kind of get more dimensionality or start representing R3, the third vector will have to break out of that plane. It would have to break out of that plane. And if a vector is breaking out of that plane, that means it's a vector that can't be represented anywhere on that plane, so it's outside of the span of those 2 vectors. Or it's outside, it can't be represented by a linear combination of this one and this one. So if you had a vector of this one, and this one, and just those 3, none of these other things that I drew, that would be linearly independent. Let me draw a couple more examples for you. That one might have been a little too abstract. So, for example, if I had the vectors 2, 3, and I have the vector 7, 2, and I have the vector 9, 5, and I were to ask you, are these linearly dependent or independent? So at first you say, well, it's not trivial. Let's see, this isn't a scalar multiple of that. That doesn't look like a scalar multiple of either of the other 2. Maybe they're linearly independent. But then if you kind of inspect them, you kind of see that if we call this V1, vector 1 plus vector 2, call this vector 2, is equal to vector 3. So vector 3 is a linear combination of these other 2 vectors. So this is a linearly dependent set. And if we were to draw it in kind of 2 space, and it's just a general idea that, let me draw it R2. There's a general idea that if you have 3 two-dimensional vectors, one of them is going to be redundant. One of them definitely will be redundant. For example, if we do 2, 3, if we do the vector 2, 3, that's the first one right there, draw it in their standard position, and I draw the vector 7, 2, the vector 7, 2, so 7, 2, right there. I could show you that any point in R2, can be represented by some linear combination of these 2 vectors. We could even do a kind of a graphical representation, but I've done that in the previous video. So I could write that the span of of v1 and v2 is equal to r2. That means that every vector here, every position here can be represented by some linear combination of these two guys. Now, the vector 9, 5, that's what 9, 5, it's right there. It is in R2. It is in R2, right? Clearly, I just graphed it on this plane. It's in our two-dimensional real number space, or I guess we could call it a space, or in our set R2. It's there. It's right there. So we just said that anything in R2 can be represented by a linear combination of those two guys. So clearly, this is in R2, so it can be represented as a linear combination. So hopefully, you're starting to see the relationship between span and linear independence or linear dependence. Let me do another example. Let's say I have the vectors. Let me do a new color. Let's have the vector, and this will be a little bit obvious, 7, 0. So that's my v1. And then I have my second vector, which is 0, minus 1. That's v2. Now, is this set linearly independent? Is it linearly independent? Well, can I represent either of these as a combination of the other? And really, when I say as a combination, you would have to scale up one to get the other, because there's only two vectors here. If I'm trying to add up to this vector, the only thing I have to deal with is this one, so all I can do is scale it up. Well, there's nothing I can do, no matter what I multiply this vector by, some constant, and and add it to itself or scale it up. This term right here is always going to be 0. It's always going to be 0. So nothing I can multiply this by is going to get me to this vector. Likewise, no matter what I multiply this vector by, the top term is always going to be 0. So there's no way I could get to this vector. So both of these vectors, there's no way that you can represent one as a combination of the other. So these two are linearly independent. And you can even see it in, if we graph it, one is 7, 0, which is like that. We do it in a non-yellow color. 7, 0, and one is 0, minus 1. One is 0, minus 1. And I think you can clearly see that if you take a linear combination of any of these two, you can represent anything in R2. So the span of these, just to kind of get used to our notion of span of V1 and V2, is equal to R2. Now, this is another interesting point to make. I said the span of V1 and V2 is R2. Now, what is the span of V1, V2, and V3 in this example up here? I already showed you that this third vector can be represented as a linear combination of these two. It's actually just these two summed up. I could even draw it right here. It's just those two vectors summed up. So clearly can be represented as a linear combination of those two. So what's its span? Well, the fact that this is redundant means that it doesn't change its span. It doesn't change all of the possible linear combinations. So its span is also going to be R2. It's just that this was more vectors than you needed to span R2. R2 is a two-dimensional space, and you needed two vectors. So this was kind of a more efficient way of providing a basis. And I haven't defined basis formally yet, but I just want to use it a little conversationally, and then it'll make sense to you when I define it formally. This provides a better basis, or this provides a basis, kind of a non-redundant set of vectors that can represent R2. While this one right here is redundant. So it's not a good basis for R2. Let me give you one more example in 3 dimensions. And then the next video, I'm going to make a more formal definition of linear dependence or independence. So let's say that I had the vector, let me say 2, 0, 0. I'll make a similar argument that I made up there. And the vector 2, 0, 0, the vector 0, 1, 0, and the vector 0, 0, 7. Now, we're now in R3, right? Each of these are 3-dimensional vectors. Now, are these linear dependent or linearly independent? So are they linearly dependent or independent? Well, there's no way with some combination of these two vectors that I can end up with a non-zero term right here to make this third vector, right? Because no matter what I multiply this one by and this one by, this last term is going to be 0. So this is kind of adding a new direction to our set of vectors. Likewise, there's nothing I can do. There's no combination of this guy and this guy that I can get a non-zero term here. And finally, no combination of this guy and this guy that I can get a non-zero term here. So this set is linearly independent. Linearly independent. And if you were to graph these in 3 dimensions, you would see that none of these, these three do not lie on the same plane. Obviously, any 2 of them lie on the same plane, but if you were to actually graph it, you get 2, 0. Let me say that that's the x-axis. That's 2, 0, 0. Then you have this 0, 1, 0. Maybe that's the y-axis. And then you have 0, 0, 7. It looks something like this. So it almost looks like your 3-dimensional axes. It almost looks like the vectors I, j, k. They're just scaled up a little bit. But you can always correct that by just scaling them down, right? Because we care about any linear combination of these. So the span of these 3 vectors right here, because they're all adding new directionality, is R3. Anyway, I thought I would leave you there in this video. I realize I've been making longer and longer videos, and I want to get back in the habit of making shorter ones. In the next video, I'm going to make a more formal definition of linear dependence, and we'll do a bunch more examples.
Okay, ba.
Let's say I had the vector
Okay, ba. Okay, ba. Okay ပါအမှန်မှန်တော့ဒီမှာဆိုရင်ဒီမှာသူပြောတဲ့ဒီ linearly dependent ဖြစ်တဲ့ဟာရဲ့ independent ဖြစ်တဲ့ဟာကိုပြောထားတဲ့ပုံစံမျိုးပေါ့နော်ဒီဟာလေးကိုလည်းဆိုဒီ machine learning course မှာလည်းတွေ့ကြရတယ်ပေါ့ဒါပေမဲ့သိပြီးနားမလည်လိုက်ကြတော့သူကဘာကိုပြောချင်လဲပါတယ်ဆိုတာပေါ့နော်ဒီဟာကိုကြည့်မယ်ဆိုပို့ပြီးတော့နားလေးပို့ပြီးရှင်းသွားတယ်ပေါ့နော်ဒီမှာဆို span ဆိုတဲ့ concept ကမနေ့ကအဲ့လိုနားထောင်ကြရတယ်ပေါ့နော်သူကဖြစ်နိုင်ဒီ span နဲ့ပတ်သက်ပြီးသူပြောရတဲ့ဟာလေးကမျက်စိနဲ့မြင်အောင်ပြောမယ်ဆိုရင်လည်းဆိုဒီဟာလေးကိုပို့ပြီးတော့မြင်သွားတယ်ပေါ့နော်သူပြောတဲ့ span ဆိုတဲ့သဘောတရားကိုအဲ့ဒါဆိုဘာမှပြောလို့မြင်သွားလဲဆိုတော့ခဏနော်ဒီနှစ်ခုပေါ့နော်ဒီနှစ်ခုကြားထဲမှာဒီနှစ်ခုတွေကြားထဲမှာဖြစ်လာတဲ့ဟာအားလုံးပဲသူကဒါဒီ line ကသူ infinity direction ကြီးသွားလို့ရတယ်ကွာဒီမှာဆိုဒီ line အဲ့လိုမျိုးတို့နှစ်ခုကြားရဒီဟာအားလုံး possible outcome တွေပေါ့နော် linear combination အားလုံးကွာ span လုပ်လိုက်တဲ့ပုံစံမျိုးအဲ့ဘောတရားကိုပြောချင်တာပေါ့နော်ဒီမှာ span ဆိုတာလေအဓိကဒီမှာသူပြောသွားတာဒီ beta နှစ်ခုကသူတို့နှစ်ခုက dependent ဖြစ်လားဒါမှမဟုတ် dependent မဖြစ်ဘူးလားဆိုတဲ့အကြောင်းပြောသွားတယ်ပေါ့နော်ဒီမှာဆိုရင်လုံးဝသူက dependent ဖြစ်တယ်ဆိုရင်ဒီကိုယ့်ရဲ့ beta နောက်တစ်ခုနဲ့ကိုကြိုက်သလို transform လုပ်လို့ရတယ်ဒီ beta A ပဲထားပါတော့ A ကနေ B1 ပဲထားပါတော့ B1 နဲ့ B2 ကို transfer လုပ်ချင်လို့လုပ်လို့ရတယ်ဒီမှာဆိုရင် B1 နဲ့ဒါ B1 ကိုခေါ်ရနော် B1 နဲ့ပြီးတော့ B2 ပြောင်းနေနည်းနည်းမြောက်လိုက်ရုံပဲကွာအဲ့လိုမျိုးလေးတွေပေါ့နော်တစ်ခုရဲ့နောက်တစ်ခု transfer လုပ်လို့ရတဲ့ဟာမျိုးလေးပုံစံ transfer ကိုပြောကြတာနော်အဲ့ဒီနေရာမှာ transfer လုပ်လို့ရတဲ့ဟာမျိုးပြောချင်တဲ့သဘောပေါ့နော် linearly dependent ဖြစ်တဲ့ဟာတွေက transform လုပ်လို့ရတယ်ပေါ့နော်ဒီမှာဆိုရင် linearly independent ဖြစ်တဲ့ဟာလေး Isabel လေးနဲ့ပြောသွားဒီမှာဆိုဒီဟာလေးဆိုရင်ဒါ 2D မှာပေါ့နော် linearly dependent ဖြစ်တဲ့ဟာတွေပေါ့ဆိုတော့ဒီမှာဆိုရင်တော့ဘယ်လောက်ဒီ value ကနေဒီကို transfer လုပ်ဖို့အတွက်အရန်ခတ်တယ်ပေါ့နော်ဒီမှာ0ဖြစ်တဲ့အတွက်ဒီသူက0လိုတာဖြစ်တဲ့အတွက်ပေါ့နော်ဒီမှာပြောနေတာဒီနေရာမှာကြည့်မယ်ဆိုရင်ဒီဟာ0ရဖို့အတွက်ဆိုရင်လည်းဟာသူဘယ်လောက်များများတော့0ဖြစ်နေမှာဒီမှာ -1 ဖြစ်တဲ့အတွက်သူ0ဘယ်မှပြောင်းလို့မရဘူးဖြစ်နေဒီထုံးစံအတိုင်းပေါ့နော်ဒီနေရာလေးကအဲ့လိုမျိုးဒီကနေဒီဟာကိုသုံးပြီးတော့ဒီဘက်ကိုသွားလို့မရတယ်ဆိုတဲ့အကြောင်းကိုသူပြောထားတယ်ပေါ့နော်ဒီကနေသုံးပြီးတော့ဒီဘက်ကိုသွားလို့မရဘူးအဲ့လိုမျိုးဒီနှစ်ခုအဲ့လိုမျိုးနှစ်ခုဖြစ်နေတဲ့ factor ကိုဘာခေါ်လဲဆိုတော့ linearly independent ဖြစ်တယ်ဆိုတဲ့အကြောင်းကိုသူပြောထားတယ်ပေါ့နော်ဒီဟာလေးနဲ့ပတ်သက်ပြီးနည်းနည်းရှင်းလာလားမသိဘူးမောင်လေးညီမလေးတို့အဆင်ပြေကြလားဒီနှစ်ခုသူပြောပါလေညီမအိမ်မအဆင်ပြေလားညီမ
ဟုတ်ကဲ့အဲ့ဒါ
Okay မောင်လေးခိုင်နေရောအဆင်ပြေလားမောင်လေးအဲ့နားလေလား linearly dependent နဲ့ independent ဆိုဘာကိုပြောချင်လဲဆိုတာလေးလေဒီစီလည်းမြင်လာတာနည်းနည်း Hello မောင်လေးကြားလားမသိဘူးအတက်မထွက်လာအောင်နော်ဘာလို့ထားလိုက်ပါတော့မောင်လေးကြော်သူကမောင်လေးနားလေလာတာ
ရတယ်
ဟုတ်ကဲ့ပါကိုဖြိုးရောနားလေလားကိုဖြိုးနဲ့ရှင်းလား
ဟုတ်ကဲ့
ပြောချင်တဲ့ဟာနားရှင်းလားသူဟိုမှာတော့သူပြောပါတော့ဒီ linearly dependent ဖြစ်တယ်အဲ့ဒါဆို R နဲ့ရှာပြီး R လို့သူသုံးသွားအဲ့မှာ constant တစ်ခုနဲ့မြောက်လိုက်တာလို့ပေါင်းလိုက်တာအဲ့လိုဥစ္စာတွေပေါ့နော်အရင်ဥစ္စာတွေမှာဆိုရင်လေအဲ့လိုဆိုတော့ဒီညမှာဒီဟာလေးပို့ပြီးမျက်စိနဲ့မြင်လာမယ်လို့မြင်တယ်ပေါ့နော်ဒီဟာလေးပတ်သက်ပြီးတော့ဟုတ်ပြီမဆွေတော့မှနည်းနည်းရှင်းလာတာဒီဟာလေးကိုသူပြောချင်တဲ့ဟာလေ
ရှင်းတယ်ဟိုဒီ R2 နဲ့မြောက်တဲ့ဟာပါလေဟိုအောက်ကလေဟို700 -1 လေ
အမှာ
အဲ့မှာဟိုပါလေဟိုဘက်ဘေးနားမှာ R2 နဲ့မြောက်တော့အဖြေရတယ်အဲ့ဒါဘယ်လိုရရလဲမသိ
R2 နဲ့မြောက်တဲ့အပြေကမြောက်လိုက်တာဘယ်မှာ okay နော်အဲ့ဒီဟာလေးကအောက်ကဟာလေးလားအပေါ်ဟာလေးလားဒီဟာလေးလား
အလဲကောင်ကဟာလေးသားလို့
ဟာလေးနော်အမှန်သူကဒီဟာက R2 span ထဲမှာရှိတယ်လို့ပဲသူကပြောထားတာမြောက်ထားတဲ့သဘောပြောတာမဟုတ်ဘူးအမှန်သိလားဘယ်လိုလဲဆိုတော့ကွာဒီဟာကိုသူ represent လုပ်တဲ့ခါကျရင်သူ R2 ထဲမှာပဲရှိမယ်ဒါပေမဲ့ဒီနှစ်ခုလုံးရအောင်သူလုပ်လို့မရအောင်ဆိုတဲ့အကြောင်းပဲသူအဓိကပြောတာမြောက်တယ်ဆိုတဲ့သဘောကိုပြောတာမဟုတ်ဘူးသိလားမမဒီမှာဆိုရင်the possible combination တွေကဘာတွေဖြစ်နိုင်လဲဆိုတော့ R2 dimension ထဲမှာဖြစ်နိုင်တယ်ဆိုတဲ့အကြောင်းသူပြောပြထားတယ်ပေါ့နော်ဒီ V3 ကသူဘာလို့မထည့်လဲဆိုတော့ V3 ကလည်း R2 dimension ဒီထဲမှာပဲဖြစ်နေတာဖြစ်တဲ့အတွက်သူက redundant ဖြစ်တယ်ဆိုတော့အပေါ်လိုဖြစ်နေတယ်ဆိုတဲ့သဘောကိုသူကပြောတာဖြစ်တဲ့အတွက်ဒီဘက်ကနှစ်ခုပဲသုံးပြီးတော့သူကဒီ R2 ကိုဆွဲလို့ရတယ်ပေါ့နော်အဲ့လိုမျိုးမဟုတ်လဲ R3 ကထိတ်နေဒီဟာပဲပြန် same result ပဲထွက်လာတယ်ဆိုတဲ့အကြောင်းလည်းသူပြောထားတယ်ဒီမှာဆိုR3 ကလည်းဒီ V3 ကလည်းဒီဟာလို့ပဲသူပြောတာဆိုတော့သူက already inside ကွာဒီ V1 နဲ့ V2 ရဲ့ inside တဲ့ span ထဲမှာရှိနေတဲ့အတွက်သူ redundant ဖြစ်နေတယ်ဒီတော့ represent လုပ်ကြမလို့ဆိုတဲ့အကြောင်းလေးပြောတာအမmultiply လုပ်တာတော့မဟုတ်ဘူးနည်းနည်းရှင်းနော်ဟုတ်ပြီအခုရဲမြောက်အခုအဆင်ပြေလားဒီ linear dependent နဲ့ independent ဆိုတာဘာကိုပြောချင်လဲကဲပါအခုအဆင်မပြေတမ်းစမြောက်ညီမရင်ထိုးညီမအဆင်ပြေလား
ဟုတ်အဆင်ပြေပါတယ်
နောက်တစ်ခုသွားကြအောင်နော်ရကြသူ linear dependent နဲ့ပတ်သက်တဲ့ example လေးပို့ပေးကြမှာနော်မျက်စိနဲ့ clear လေးမြင်လာအောင်ဒါသူပြောသူ short video တွေပဲလုပ်တော့မှပြောကြည့်ဒီမှာဆို18မိနစ်တာနော်ဒါ short video လေးလားလိုက်လို့သူ
reasonable sense of what linear dependence means. So let's just do a slightly more formal definition of linear dependence. So we're going to say that a set of vectors, let me just define my set of vectors. So let me call my set S of vectors v1, v2, all the way to vn. So I'm going to say that they are linearly dependent. Linearly dependent if and only if. So sometimes it's written if with a lot of F's in there. So sometimes it's written if and only if. Sometimes it's shown like an arrow in two directions. If and only if I can satisfy this equation, I can find a set of constants. I can find a set of constants, C1 times V1. So I can take a linear combination of my vectors all the way to Cn, Vn, that satisfy the equation that I can create this into the zero vector. So sometimes it's just written as bold 0, and sometimes you could just write it. I mean, we don't know the dimensionality of this vector. You know, it'd be 0, be a bunch of zeros. We don't know how many actual elements are in each of these vectors, but you get the idea. So it's my set of vectors is linearly dependent. Remember, I'm saying dependent, not independent, is linearly dependent if and only if I can satisfy this equation for some CI's where not all of them are equal to 0. For some CI's where not all, and this is key, not all are 0. Or you could say it the other way. You could say at least one is non-zero. So how does this gel with what we were talking about in the previous video where I said, look, a set is linearly dependent if one of the vectors can be represented by the combination of the other vectors. So let me write that down. So in the last video I said, look, you know, one vector can be, well, let me write it this way. One vector being represented by the sum of the other vectors, I can just write it like this. I can write a little bit more mathy. In the last video, I said that linear dependence means that, let me just pick an arbitrary vector. V1, let's say that V1 is, you know, this is arbitrary. V1 could be represented by some combination of the other vectors. By, you know, let me call them A1 times V, let me be careful. A2 times V2 plus A3 times V3 plus all the way up to AN times VN. This is what we said in the previous video. Look, if this is linearly dependent, if any one of these guys can be represented as some combination of the other ones. So how does this imply that? And in order to show this if and only if, I have to show that this implies that, and I have to show that that implies this. So this is almost a trivially easy proof, because if I subtract v1 from both sides of this equation, I get 0 is equal to minus 1 v1 plus a2 v2 plus a3 v3 all the way to an vn. And clearly, I've just said, well, this is linear dependent. That means that I can represent this vector as a sum of the other vectors, which means that minus 1 times v1 plus some combination of the other vectors is equal to 0, which means that I've been able to satisfy this equation, and at least one of my constants is non-zero. Non-zero. So I've shown you that if I can represent one of the vectors by a sum of the other ones, then this condition is definitely going to be true. Now let me go the other way. Let me show you if I have this situation that I can definitely represent one of the vectors as the sum of the others. So let's say that this is true. Let's say that this is true, and one of these constants, remember, it's not just this, it's at least one is non-zero. So let me just assume, just for the sake of simplicity, I mean, these are all arbitrary, let me just assume, I'll do it in a new color, let me do it in the magenta, let me assume that C1 is not equal to 0. If C1 is not equal to 0, then I can just divide both sides of this equation by C1. And what do I get? I get V1 plus C2 over C1 V2 plus all the way up to Cn over C1 is equal to 0. And then I can multiply both sides of this by, or I could add negative V1 to both sides of this equation, or subtract V1 from both sides, and I get C2 over C1 V2 plus all the way up to Cn over C1 Vn, so Vn here, is equal to minus V1, is equal to minus V1. Now if I just multiply both sides of this by negative 1, I get a minus, and all these become minuses, and this becomes a plus. And I just showed you that if at least one of these constants is non-zero, that I can represent my vector V1 as some combination of the other vectors. So we're able to go this way too. If this condition is true, then I can represent one of the vectors as a combination of the others. If I can represent one of the vectors as a combination of the others, then this condition is true. So hopefully that kind of proves that these two definitions are equivalent. Maybe it's a little bit of overkill. But let's apply that definition now to actually test. You might say, hey, Sal, why did you go through all of this effort? And I went through all of this effort because this is actually a really useful way to test whether things are linearly independent or dependent. Let's try it out. Let's use our newly found tool. So let's say I have the set of vectors. Let's say I have the set of vectors. Let me do it up here. I want to be efficient with my space usage. So let's say I have the set of vectors 2, 1, 2, 1, and 3, 2. And my question to you is, are these linearly independent or are they linearly dependent? Well, in order for them to be linearly dependent, that means that there's if some constant times 2, 1 plus some other constant times this second vector, 3, 2, where this should be equal to 0, where these both aren't necessarily 0. So before I go forth this problem, let's remember what we're going to find out. If either of these are non-zero, so if C1 or C2 non-zero, then this implies that we are dealing with a linearly dependent network set. Linearly dependent. Now, if C1 and C2 are both zero, if the only way to satisfy this equation, I mean, you can always satisfy it by setting everything equal to 0, but if the only way to satisfy it is by making both of these guys 0, then we're dealing with a linearly independent set. So let's try to do some math, and this will just take us back to our Algebra 1 days. So in order for this to be true, that means 2 times C1 plus 3 times C2 is equal to, when I say this is equal to 0, it's really the 0 vector, so I can rewrite this as 0, 0. So it's equal to, so 2 times C1 plus 3 times C2 would be equal to that 0 there. And then we'd have 1 times C1, 1 times C1 plus 2 times C2 plus 2 times C2 is equal to that 0, is equal to that 0 right there. And now this is just a system, 2 equations, 2 unknowns. A couple of things we could do. Let's just multiply, let's just multiply this top equation by 1/2. And then so if you multiply it by 1/2, you get C1 plus 3 halves plus 3 halves C2 is equal to 0. And then if we subtract the green equation from the red equation, this becomes 0. 2 minus 1/2. 3 halves is 1/2. So this is just 1/2 C2 is equal to 0. And this is easy to solve. C2 is equal to 0. So what's C1? Let's just substitute this back in. C2 is equal to 0. So this is equal to 0. So C1 plus 0 is equal to 0. So C1 is also equal to 0. We're going to substitute it back into that top equation as well. So the only solution to this equation, involves both C1 and C2 being equal to 0. So they both have to be 0. So this is a linearly independent set. Of vectors, which means that neither of them are redundant of the other one. You can't represent one as a combination of the other. And since we have 2 vectors here, and they're linearly independent, we can actually know that this will span R2. This will span R2. The span of our vectors is equal to R2. If one of these vectors was just some multiple of the other, then the span would have been some line within R2, not all of them. Now I can represent any vector in R2 as some combination of those. Let's do another example. Let's say, let me scroll to the right, because sometimes this thing, when I go too far down, I haven't figured out why. When I go too far down, it starts messing up. So my next example is the set of vectors. So I have the vector 2, 1. I have the vector 3, 2. And I have the vector 1, 2. And I want to know, are these linearly dependent or linearly independent? So I do go through the same drill. I use that little theorem that I proved at the beginning of this video. So in order for these to be, well, in order for them to be linearly dependent, there must be some set of weights that I can multiply these guys. So C1 times this vector plus C2 times this vector plus C3 times that vector. That will equal the 0 vector. And if one of these is non-zero, then we're dealing with a linearly dependent set of vectors. And if all of them are 0, then it's independent. So let's just do our linear algebra. Well, actually, so this means that 2 times C1 plus 3 times C2 plus C3 is equal to that 0 up there. And then if we do the bottom rows, remember when you multiply scalar times a vector, you multiply it by each of these terms. So C1 times 1, so 1C1 plus 2C2 plus 2C3 is equal to 0. Now, there's a couple of giveaways on this problem. If you have 3 two-dimensional vectors, one of them is going to be redundant. Because in the very best case, even if you assume that, let's say that vector and that vector are linearly independent, then these would span R2, which means that any vector in your two-dimensional space can be represented by some combination of those two, in which case this is going to be one of them, because this is just a vector in two-dimensional space. So it'd be linearly dependent. And then if you say, well, these aren't linearly independent, well, then if these aren't linearly independent, then these they're just multiples of each other, in which case this would definitely be a linearly dependent set. So when you see 3 vectors that are each only vectors in R2, that are each two-dimensional vectors, it's a complete giveaway that this is linearly dependent. But I'm going to show it to you using our dependent using our little theorem here. So I'm going to show you that I can get non-zeros C3, C2s, and C1s such that I can get the 0 here. If all of these had to be 0, I mean, you can always set them equal to 0, but if they had to be equal to 0, then it would be linear independent. But let me just show you. Look, I can just pick some random C3. Let me pick C3 to be equal to -1. So what would these two equations reduce to? I mean, if you have 3 unknowns and 2 equations, it means you don't have enough constraints on your system. So if I just set C3, I just picked that out of a hat. I could have picked C3 to be anything. But if I set C3 to be equal to -1, what do these equations become? You get 2C1 plus 3C2 minus 1 is equal to 0, and you get C1 plus 2C2 minus 2 is equal to 0, right? 2 times minus 1. And then what can I do here? If I multiply this second equation by 2, what do I get? I get 2 plus 4C2 minus 4 is equal to 0. And now let's subtract this equation from that equation. So the C1s cancel out. 3C2 minus 4C2 is minus C2. And then minus 1 minus minus 4. So that's minus 1 plus 4. That's plus 3 is equal to 0. And so we get our C. Let me make sure I got that right. We have a minus 1 minus a minus 4. So plus 4. So we have a plus 3. Right. So that is a minus 2. So we have our C2 is equal to minus C2 is equal to minus 3, or C2 is equal to 3. So we get C2 is equal to 3. And if C2 is equal to 3 and C3 is equal to minus 1, let's just substitute here. So we get C1 plus 2 times C2, so plus 6, plus 2 times C3, so minus 2. Minus 2 is equal to 0. C1 plus 4 is equal to 0. C1 is equal to minus 4. C1 is equal to minus 4. So I'm giving you a combination of C's that will give us a 0 vector. If I multiply minus 4 times our first vector, 2, 1, that's C1, plus 3 times our second vector, 3, 2, minus 1 times our third vector, 1, 2, this should be equal to 0. Let's verify it just for fun. Minus 4 times 2 is minus 8, plus 9, minus 1. That's 9 plus 9, that's 0. Minus 4 times, that's minus 4, plus 6, minus 2. Minus 4 plus 6 minus 2, that's also 0. So we've just shown a linear combination of these vectors where actually none of the constants are 0, but all we had to show is that at least one of the constants had to be non-zero, and we actually showed all 3 of them were, but at least one of these had to be non-zero, and I was able to satisfy this equation. I was able to make them into the 0 vector. So this proves that this is a linearly dependent set of vectors, linearly dependent, which means one of the vectors is redundant. And you can never just say, oh, this is the redundant vector, because I can represent this as a combination of those two. You could just as easily pick this guy as the redundant vector and say, hey, these two, I can represent this guy as a sum of those two. There's not kind of one bad apple in the bunch. Any of them can be represented by the combination of some other, by all of the rest of them. So hopefully, you have a better intuition of linear dependence and independence. Maybe I'll continue. I'll do a few more examples in the next video.
ဟုတ်ပါပြီဒီဟာလေးကိုပေးရလေလက်ချက်ထားမလို့နော်မမှန်ဆိုဒီဟာလေးကအဲ့ဒါဆိုဒီဟာကိုလောက်ရတယ်ပေါ့မှတ်မိလားမသိ exercise လောက်ရတယ်လေ exercise လောက်ရတာဘယ် number ဘယ်လိုရှာမှမသိဖြစ်နေကြပါရောလား
C1 plus
ဘယ် number ကိုဘယ်လိုလောက်မှမသိဖြစ်နေတဲ့ဟာလေးလေမှတ်မိကြလားမသိ quiz ထဲမှာတစ်ခုဖြေရတယ်လေ practice quiz မှာမှတ်မိကြလားမသိ linearly dependent နဲ့ independent အဲ့ဒါဆိုဖြေခိုင်းပါရောလားအဲ့ဒါဘယ်လိုရှာတိုင်းမကိုရန်တန်းပန်းတန်းထည့်ပြီးထက်တွက်လားမှတ်မိကြလားမသိအမေသူကအဲ့လို formula လေးရှိရအောင်နော်ကိုရဲအဲ့လိုမသိလားမသိလားဆိုဖြစ်လက်တန်းတွက်ထားကြတယ်ပေါ့နော်အမှန်ဆိုဒီလိုမျိုးတွက်လို့ရတယ်ပေါ့ဒီဟာလေးက linear ဖြစ်လားမဖြစ်လားဆိုဒီမှာဆို ls note ရဆိုပေါ့နော်ဒီကလို့ဒီ vector တွေက linearly dependent ဖြစ်တယ်ဆိုရင် तू ကဒီလိုမျိုးခုနဒီလိုနေရာမဟုတ် c ကလည်း0ဒီ c2 ကလည်း 0 c1 လည်း0အဲ့လိုမျိုး0ဖြစ်စရာမလိုဘူးပေါ့နော်တခြား non zero value ရအောင်မယ်ပေါ့ တကယ်လို့ဒါသူက linearly dependent ဖြစ် non zero value independent ဖြစ်တယ်ဆိုတော့ခဏသူဒီမှာပြရတဲ့ example လေးအတိုင်းပဲပေါ့နော်အားလုံးလိုက0ဖြစ်သွားလိုက်မယ်တကယ်လို့သူကဒါဒီ vector နှစ်ခုကွာမသိဘူးကွာသူတို့နှစ်ခုက linear dependent ဖြစ်တာမဖြစ်လားဆိုတော့အဲ့လိုချတွက်လို့ရတယ်ပေါ့နော်အဲ့လိုချတွက်ရင်သူတို့ value တွေကအားလုံးလို0ဖြစ်နေဆိုတော့သူတို့က independent ဖြစ်တယ်လို့ပြောလို့ရတယ်ပေါ့dependent ဆိုရင်ဘယ်လိုဖြစ်လဲဆိုဒီ dependent ဆိုခုနကပေါ့နော်သူကဒီမှာဆိုရင်3ခုလုံးပေါ့နော်ဒါပေမဲ့3ခုလုံးကဒါ non zero value ဖြစ်ရမယ်လို့ပြောတာနော်ဒါပေမဲ့ non zero value ဒါပေမဲ့3ခုလုံးဖြစ်စရာမလိုအနည်းဆို at least one non zero value လို့သူပြောတာနော်ပြောချင်တာဒီ C1 နဲ့ C2 ကတော့00ဖြစ်ပေမဲ့လည်း C3 က0မဖြစ်ဘူးဆိုရင်ဒါကသူက linearly dependent ပြောလို့ရတယ်ဒါမှမဟုတ်လည်း C3 နဲ့ C2 နဲ့က C2 နဲ့ C1 က0ဖြစ်ပြီးတော့ C3 က0မဖြစ်ဘူးဆိုလည်းဒါ linearly dependent ဆိုပြောလို့ရတယ်ဒီကနေ့ပတ်သက်ပြီးနည်းနည်းရှင်းလာကြလားဒါမှမဟုတ်လည်း question လေးမေးစရာရှိလားလဲဆိုအဓိကဒီက formula သူပြောပြရတယ်ပေါ့နော်အစပိုင်းကနည်းနည်းရှုပ်တယ်သိရမလားအစပိုင်းကျတော့ theory ကသူပြောနေတယ်ရန် complex ဖြစ်နေတာခဏထားလိုက်ဒီကဒီမှာဆိုဒီဟာလေးဒီနှစ်ကြောင်းလေးကိုပဲမှတ်ထားမှာပေါ့နော် at least 1 non zero ဖြစ်ရမယ်ဆိုတဲ့အကြောင်းလေးရယ်ပြီးရင် all are ဟိုဒီ dependent ဖြစ်တယ်ဆိုရင် at least 1 non zero ဖြစ်ရမယ် independent ဖြစ်တယ်ဆိုရင် sorry independent ဖြစ်တယ်ဆိုရင်တော့အကုန်လုံးလိုက0ဖြစ်ရမယ်အဲ့ဒါလေးကိုတစ်ချက်ပေါ့နော်သူဒီ formula လေးကိုမြင်စီတယ်ဒီဟာလေးသူပြောတဲ့ဟာလေးနည်းနည်းမမြင်စီတယ်မြင်အောင်ပေါ့နော်သူကအဓိကသူဘာကိုရှာနေလဲဆိုတော့အဲ့ဒါဆို machine learning နဲ့ပြန်ပြီး concept ကိုပြန်ပြီး map လုပ်ရမယ်ဆိုရင်ပေါ့နော်ဒီ new information က redundant ဖြစ်နေလားဒါမှမဟုတ်ဒီ information ကိုငါ skip လုပ်လိုက်လို့ရလားလို့ဆိုတော့ electro ကကိုယ့်ရဲ့ neural network ကိုမပေးတဲ့ခါကျရင်ဒီ metric data တွေပေးမှာဟုတ်တယ်ဟုတ်တချို့ metric တွေက sorry တချို့ metric တွေကကြတော့ကွာဒါအရင်ကိုယ့်ရဲ့ network အတွက်အသုံးမလိုတဲ့ဟာတွေလည်းဖြစ်ကောင်းဖြစ်နိုင်တယ်ပေါ့နော်အဲ့လိုဆိုရင်ဒီဟာ redundant ဖြစ်နေတာ redundant ဆိုတာဒီမှာကွာပို့ဖြစ်နေလားဒီဟာကိုငါဒီ information ငါမသုံးမဲ့နောက်တစ်ခုနဲ့ငါအစားထိုးလို့ရတာအဲ့လိုဟာမျိုးလေးပြောနေတာပေါ့နော်အဲ့လိုမျိုးဆိုတော့ကို model အတွက်ဆိုရင်ဒီ redundant ဖြစ်တဲ့ဟာလေးတွေကပိုကောင်းတယ်ပေါ့နော် information ပိုစုံရတယ်ပေါ့ပိုပြီး train လုပ်ရတာပိုအဆင်ပြေတယ်ပေါ့နော်အဲ့ဒါမျိုးလေးကိုဒါနောက်ပိုင်းကျရင်သူသုံးချမယ်ဒီ dependent ဖြစ်တာလားမဖြစ်တာလားအဲ့လိုမျိုးနောက်ပိုင်းကျရင်သုံးချမလားမသိဘူးပေါ့နော်ဒါအဲ့လိုမရှိတယ်နည်းနည်းမြင်တာလေးပြောပြတာမောင်လေးတို့ညီမလေးတို့က question လေးမေးကြရှိလားဒီဟာလေးနဲ့ပတ်သက်ပြီးတော့ဟုတ်ကဲ့မဆိုတဲ့မေးကြရှိလားမ
မရှိဘူးညီမလေး
ဟုတ်ကဲ့ကိုကျော်သူကစင်နေတာမောင်လေးကျော်သူဟုတ်ကဲ့တော့ဘာလို့ကိုရင်မောင်လေးခေါ်
မရှိဘူး
ကဲကျော်သူကခေါ်လိုက်တယ်နော်ဟုတ်
ရတယ်မရ
ဟုတ်ပါလေရောအစင်ပြေတယ်ဟုတ်ဟိုအစင်ပြေတော့အဲ့ဒါညီမရင်ဟိုညီမအစင်ပြေလားညီမ
ဟုတ်ပြေပါတယ်
ကိုတို့ကမှ join လာလားခုနကိုတို့ဒီပြတ်တယ်ပဲโอเคပါမောင်လေးပြောအဆင်ပြေတယ်โอเคအဲ့ဒါဆိုနောက်တစ်ခုသွားကြအောင်မနော်ဒီခုနကဒါသူ exhibit နည်းနည်းပေးမယ်ပေါ့ miss တယ်မြင်လာအောင်သူနောက်တစ်ခု exhibit ထပ်ပေးမယ်ဆိုတော့ကြည့်အောင်ဘယ်လောက်ကြာလဲပေါ့နော်သူက short video ပါဆိုတော့16မိနစ်โอเคဟုတ်ပါပြီအဲ့ဆိုဒီနေ့တော့ဒီဟာလေးပြီးရတိလောက်ကြမှာနော်ကြည့်အောင်ဟုတ်ပြီ
the span of a set of vectors together in one particularly hairy problem because if you understand what this problem is all about I think you understand what we're doing which is key to your understanding of linear algebra these two concepts so the first question I'm going to ask about this set of vectors S and they're all three-dimensional vectors they have three components is the span of S is that equal to R3 and it seems like it might be. If each of these add new information, it seems like maybe I could describe any vector in R3 by these three vectors, by some combination of these three vectors. And the second question I'm going to ask is, are they linearly independent? And maybe I'll be able to answer them at the same time. So let's answer the first one. Do they span R3? And to span R3, that means some linear combination of these three vectors should be able to construct any vector in R3. So let me give you a linear combination of these vectors. So I could have C1 times the first vector, 1, minus 1, 2, plus some other arbitrary constant C2, some scalar, times the second vector, 2, 1, 3, plus some third scaling factor times the third vector, minus 1, 0, 2, I should be able to, using some arbitrary constants, take a combination of these vectors that sum up to any vector in R3. And I'm going to represent any vector in R3 by the vector A, B, and C, where A, B, and C are any real numbers. So if you give me any A, B, and C, and I can give you a formula for telling you what your C3s, your C2s, and your C1s are, then that essentially means it spans R3. Because if you give me a vector, I can always tell you how to construct that vector with these three. So let's see if I can do that. So just from our definition of of scalar multiplication of a vector, we know that C1 times this vector, I could rewrite it if I want. I normally skip this step, but I really want to make it clear. So C1 times this, I could just rewrite it as 1 times C, it's each of the terms times C1. Similarly, C2 times this is the same thing as each of the terms times C2. And C3 times this is the same thing as each of the terms times C3. I want to show you that everything we do, it just formally comes from our definition of vector, of multiplication of a vector times a scalar, which is what we just did, or vector addition, which is what we're about to do. So vector addition tells us that this term plus this term plus this term needs to equal that term. So let me write that down. We get C1 plus 2C2 minus C3 will be equal to A. Likewise, we can do the same thing with the next row. Minus C1 plus C2 plus 0 C3 must be equal to B. So we get minus C1 plus C2 plus 0 C3, so we only have to write that, is going to be equal to B. And then finally, let's just do that last row. 2C1 plus 3C2 plus 3C2 plus 2C3 plus 2C3 is going to be equal to C right there. Now let's see if we can solve for our different constants. So I'm going to do it by elimination. I think you might be familiar with this process. I think I've done it in some of the earlier linear algebra videos before I started doing a formal presentation of it. And I'm going to review it again in a few videos from now, but I think you understand how to solve it this way. What I'm going to do is I'm going to first eliminate these two terms, and then I'm going to eliminate this term, and then I can solve for my various constants. So if I want to eliminate this term right here, what I could do is I could add this equation to that equation, or even better, I can replace this equation with the sum of these two equations. So let me do that. So I'm just going to add these two equations to each other and replace this one with that sum. So minus C1 plus C1, that just gives you 0. I can ignore it. Then C2 plus 2C2, that's 3C2, and then 0 plus minus C3 is equal to minus C3. Minus C3 is equal to, and I'm replacing this with the sum of these two, so B plus A, it equals B plus A. Let me write down that first equation on the top. So the first equation, I'm not doing anything to it. So I get C1 plus 2C2 minus C3 is equal to A. Now in this last equation, I want to eliminate this term. So let's take this equation and subtract from it 2 times this top equation. So minus 2 times so you could also view it as, let's add this to minus 2 times this top equation. And since we're almost done using this, we actually even wrote it, let's just multiply this times minus 2. So this becomes a minus 2C1 minus 4C2 plus 2C3. So plus 2C3 is equal to minus 2A, right? If you just multiply each of these terms, I want to be very careful. I don't want to make a careless mistake. Minus 2 times C1, minus 4, plus 2, and then minus 2. And now we can add these two together, and what do we get? The 2C1 minus 2C1, that's a 0. Don't have to write it. 3C2 minus 4C2, that's a minus C2. And then you have your 2C3 plus another C2C3. So that is equal to plus 4C3 is equal to C minus 2A. C minus 2A. All I did is I replaced this with this minus 2 times that. I got this. Now I want to eliminate. Now I'm going to keep my top equation constant again. I'm not going to do anything to it, so I'm just going to move it to the right. So I get C1 plus 2C2 minus C3 is equal to A. I'm also going to keep my second equation the same. So I get 3C2 minus C3 is equal to B plus A. Let me scroll over a good bit. And then this last equation I want to eliminate. My goal is to eliminate this term right here. So what I want to do is I want to multiply this bottom equation times 3 and add it to this middle equation to eliminate this term right here. So if I multiply this bottom equation times 3, let me just do, well, actually, I don't want to make things messier. So this becomes a minus 3 plus a 3, so that those cancel out. This becomes a 12 minus a 1, right? So that becomes, so this becomes 12C3 minus C3, which is 11C3. And then this becomes a, oh, sorry, I was already done. When I do 3 times this plus that, those canceled out. And then when I multiply 3 times this, I get 12C3 minus a C3. So that's 11C3. And I multiplied this times 3 plus this. So I get 3C minus 6A, right? I'm just multiplying this times 3 plus this, plus B plus A. And so what can I rewrite this by? Actually, I want to make something very clear. This C is different than these C1, C2s, and C3s that I had up here. And I think you realize that, but I just realized that I used the letter C twice, and I just didn't want any confusion here. So this C that doesn't have any subscript is a different constant than all of these things over here. So let's see if we can simplify this. So we have an A and a minus 6A, so let's just add them. So let's get rid of that A, and then this becomes minus 5A. So we get, and then if we divide both sides of this equation by 11, what do we get? We get C3. C3 is equal to 1 over 11 times 3C minus 5A. So you give me any A or a C, and I'll already tell you what C3 is. Now, what is C2? C2 is equal to, let me simplify this equation right here. Let me do it right there. So if I just add C3 to both sides of this equation, I get 3C2 is equal to B plus A plus C3. Well, I know, and if I divide both sides of this by 3, I get C2. C2 is equal to 1 over 3 times B plus A plus C3. I'll just leave it like that for now. And then what is C1 is equal to? Well, if I could just rewrite this top equation as, if I subtract 2C2 and add C3 to both sides, I get C1 is equal to A minus 2C2 plus C3. So what have I just shown you? You can give me any vector in R3 that you want to find. So you can give me any real number for A, any real number for B, any real number for C. And if you give me those numbers, I'm claiming now that I can always tell you some combination of these 3 vectors that will add up to those. And I've actually already solved for what I have to multiply each of those vectors by to add up to this third vector. So you give me your A's, B, and C's. I just have to substitute into the A's and the C's right here. And oh, sorry, I forgot this B over here. There's also a B. It was suspicious that I didn't have to deal with the B. So this is there was a B right there. So this is 3C minus 5A plus B. Let me write that, plus a B. There's a B right there in a parentheses. But I think you get the general idea. You give me your A, B's, and C's. Any real numbers can apply. I'm not dividing by, there's no division over here, so I don't have to worry about dividing by 0. So this is just a linear combination of any real numbers, so I can clearly get another real number. So you give me your A, B's, and C's, I'm going to give you a C3. Now, you gave me A, B's, and C's, I got a C3. This is just going to be another real number, and I'm just going to take that with your former A's and B's, and I'm going to be able to give you C2. And then I already we already were able to solve for a C2 and a C3, and then I just use your A as well, and then I'm going to give you a C1. So hopefully you're seeing that no matter what A, B, and C you give me, I can give you a C1, C2, or C3. There's no reason that any A, B's, or C's should break down these formulas. We're not doing any division, so it's not like a 0 would break it down. So I can say definitively that the set of vectors of these 3 vectors does indeed span R3. Now let me ask you another question, where I already asked it. are these vectors linearly independent? Are they linearly independent?
Yep.
Now, we said that in order for them to be linearly independent, the only solution to, C1 times my first vector, 1 minus 1, 2, plus C2 times my second vector, 2, 1, 3, plus C3 times my third vector, minus 1, 0, 2. So if something is linearly independent, that means that the only solution to this equation, so if I take any there's the only solution to this equation. So if I want to find some set of combinations of these vectors that add up to the 0 vector, and I did that in the previous video, if they are linearly dependent, there must be some non-zero solution. So one of these constants, at least one of these constants, would be non-zero for this solution. I mean, you can always make them 0 no matter what, but if they're linearly dependent, then one of these could be non-zero. If they're linearly independent, then all of these have to be, the only solution to this equation would be C1, C2, C3 all have to be equal to 0. C1, C2, C3 all have to be equal to 0. Linear independence implies this. This implies linear independence. Now, this is the exact same thing we did here, but in this case, I'm just picking my A, B's, and C's to be 0. This is A, this is B, and this is C, and this is C, right? I can pick any vector in R3 for my A's, B's, and C's. I'm now picking the 0 vector. So let's see what our C1, C2s, and C3s are. So my A equals B is equal to C is equal to 0. I'm setting it equal to the 0 vector. What linear combination of these 3 vectors equal the 0 vector? Well, if A, B, and C are all equal to 0, that term is 0, that is 0, that is 0. You have 1/11 times 0 times 0 minus 0 plus 0. That's just 0. So C3 is equal to 0. Now, C3 is equal to 0. We already know that A is equal to 0 and B is equal to 0. C2 is 1/3 times 0, so it equals 0. Now, what's C1? What's C3, which is 0? C2 is 0, so 2 times 0 is 0. So C1 is just going to be equal to A. What I just said, A is equal to 0. So the only solution to this equation right here, the only combination that the only linear combination of these 3 vectors that result in the 0 vector are when you weight all of them by 0. So I just showed you that C1, C2, and C3 all have to be 0. And because they're all 0, we know that this is a linearly independent set of vectors. Or that none of these vectors can be represented as a combination of the other 2. None of these vectors can be represented as a combination of another 2. So this is interesting. I have exactly 3 vectors that span R3 and they're linearly independent. And linearly independent, in my brain, that means that, look, I don't have any redundant vectors, anything that could have just been built with the other vectors. And I have exactly 3 vectors and it's spanning R3. So in general, and I haven't proven this to you, but I could, is that if you have exactly 3 vectors and they do span R3, they have to be linearly independent. If they weren't linearly independent, then one of these would be redundant. Then, let's say that guy was a redundant one. I always pick the third one. But let's say this guy would be redundant, which means that the span of this would be equal to the span of these 2, right? Because if this guy is redundant, he could be part of the span of these 2 guys. And the span of 2 vectors could never span R3. Or in the other way you could go, if you have 3 linear independent, 3 tuples, and they're all independent, then you can also say that spans R3. But I haven't proven that to you, but hopefully you get the sense that like each of these is contributing new directionality, right? One is, going like that. They're not completely orthogonal to each other, but they're giving us enough directionality that you can kind of add a new dimension to what's going on. So hopefully that helped you a bit, and I'll see you in the next video.
Ok, bà biết lên cái thằng này nó. ကဲပါကျေးဇူးတင်ပါတယ်ညီမအီမိုတယောက်ကြံနေတယ်နော်ဟုတ်ကဲ့ပါအမှန်ဆိုဒီနေရာလေးကဒီမှာဆိုရင် तू အဓိကတွက်ပြတာပေါ့နော်အဲ့လဲဆိုတေချာလေးမျက်စိနဲ့မြင်လာအောင်ဒီဟာတော့အရင်ကြီးတော့ခေါင်းစားမဲ့ဟာလောလဲဆိုမမြင်ဘူးပေါ့နော်ဒီဟာဆိုရင်အဲ့ဆိုဒီ algebra တက်လူတွေအကုန်လုံးတွက်တာမှာပါအရင်ရောခက်တဲ့ဟာမျိုးမဟုတ် तू proof theory သူ proof ပြနေတာပေါ့နော်ကိုယ်တွေကိုလုံးဝကိုယ်လက်ခံတာတော့ miss လုပ်နေတဲ့ပေါ်ပေါ့နော် तू ပြောချင်တာဒီလိုဒီဘက်တာ3ခုက R2 span လား R3 span လား तू ပြောချင်တာခုနမတ်ဆွေမေးရပါလားခုနကဘက်တာလေးနှစ်ခုကကြာသူ R2 span ပဲရှိရဆိုသူပြောရတယ်ဒီမှာဘက်တာ3ခုရောသူက R2 span လား R3 span ဖြစ်မဖြစ်ကိုသိချင်တာပေါ့နော်ဒါ R2 span ပဲဆိုရင်သူကနောက်ထပ်တစ်ခုပဲဒါရတယ်သူက redundant ဖြစ်နေဆိုသူပြောတာပေါ့ဒါ R3 span ဆိုတာ3ခုလုံးကအရေးကြီးတဲ့ information တွေပါနေပေါ့နော်ကိုအတွက်ဒီလိုလား span က R2 မဟုတ်ပဲ R3 မဟုတ်ပဲ R2 လို့ဆိုရင်ပြောချင်တာတစ်ခုကတော့ကွာမလိုအပ်တဲ့ information တွေရှိနေပေါ့နော်ကွာဒါမသုံးလို့ရတယ်ဆိုတော့ဒီ information ကဒီဟာ duplicate ပေါ့နည်းနည်း constant တစ်ခုနဲ့မြောက်လိုက် information ကွာ generate လုပ်လို့ရတာဖြစ်တယ်အရင်အေးမပါဘူးပေါ့ဒီလိုဒါပေမဲ့ဒီ information ကသူကအရေးပါလာမပါလား redundant ဖြစ်ဖြစ်အဓိကသိချင်တာပေါ့နော်ဒီလိုမျိုးအဓိက span နဲ့ကြည့်တာတော့ linearly dependent ဖြစ်ဖြစ်အဓိကဒီနှစ်ခုရဲ့ reason တွေကပါလဲဆိုတော့နောက်ဆုံးလေးမှာသူအဓိကပြောသွားတယ်ဒီဟာလေးအဓိက linearly dependent ဖြစ်တဲ့ဟာ independent ဖြစ်တဲ့ဟာပိုကောင်းတယ်ပေါ့နော်အဲ့လဲဆိုဒီ data တွေနဲ့ဒီ information တွေရတဲ့ခါကျရင်သူက linearly independent ဖြစ်တယ်လေကိုယ်အတွက် information များရှိနေပေါ့နော် dependent ဖြစ်တယ်ဆိုရင်ဒီဟာကိုကွာနောက်တစ်ခုနဲ့ generate လုပ်လို့ရတာဖြစ်တဲ့အတွက်တိတ်ပြီးရေးမပါတဲ့ဟာမျိုးလေးဖြစ်သွားတဲ့ပုံစံမျိုးလေးပေါ့နော်ဒါ intuition တွေရတဲ့ပြောပြတာဒီကတော့နည်းကတော့အရင်ခတ်တယ်လို့လည်းဆိုရင်မောင်လေးညီမလေးတို့ကဒါ brain ကောင်းတဲ့လူတွေဖြစ်တဲ့အတွက်လုံးဝ LS တောင်တက်မဲ့လူတွေပါတဲ့အတွက်ပေါ့နော်အရင်လည်းကောင်းမစားတော့ဒီဟာလေးနဲ့ပတ်သက်ပြီးနည်းနည်း question လေးတွေမေးကြရှိပါတယ် let's go အဆင်ပြေလားညီမတို့မောင်လေးတို့မဆွေစင်တို့အမတက်ဝဲပါလာဆိုတန်းလူတွေကလုံးမောင်လေးတွေပဲဆိုတော့အဆင်ပြေကြလားကိုပြည့်အဆင်ပြေလားကိုပြော
ဟုတ်ပြေတယ်အမ
နည်းနည်းနားလေလာလားဟိုသူတို့ဒီ machine learning နဲ့ပတ်သက်တဲ့ course တွေဒီဟာလေးနည်းနည်းရှင်းကြည့်လားတချို့ဟာလေးဒီလိုကိုရှင်းတာဒီဟာလေးလေမင်းတော့နေရပါလားရှင်းလာလား
ရှင်းတယ်အမဟုတ်ရှင်း
တယ်မြောက်ကိုနည်းနည်းရှင်းလာလား
ဟုတ်ရှင်းတယ်
တော်သူရောတော်သူထုံးအောင်အဆင်ပြေလားမောင်လေးဘယ်လိုလဲမနေ့ကလည်းတမ်း
ပြေမှပြေ
အဆင်ပြေလားလိုက်ပြေတယ်မနေ့ကဟာလေးနည်းနည်းပြဿနာတက်တော့မောင်လေးလည်းအဲ့ဒါဆိုအာနာ
ရပါတယ်
ကဲပါအဲ့ဆိုနောက်တစ်ခုသွားမယ်နော်ဒီနေ့ကလည်းဒီဟာလေးတော့အဲ့ဒီ basic ဆိုတဲ့အကြောင်းလေးတွေသူပြောထားတယ်ပေါ့နော်ဒီ machine learning course မှာအဲ့ဆို basic ဆိုဘာမှမသိဘူးဖြစ်နေတာဘာကိုပြောချင်မှမသိဘူးဖြစ်နေဒီဟာလေးပြန်လုပ်ကြအောင်နော်ဒီနှစ်ခုလေးပြန်လုပ်ကြမယ်ပေါ့နော်ဒီနေ့က OMG 23မိနစ်တစ်ခုတွေအရင်ကြာနေတယ်လုပ်ချင်တယ်မောင်လေးစားဆက်သွားမလားဆက်မသွားလားဘယ်ညဒီပို့ရအောင်ဘယ်သူသွားချင်တဲ့လူပဲများရှိတယ်နောက်နေ့နေရ lesson တစ်ခုသွားမလားဒီနေ့ပဲဆက်သွားချင်လားလက်ထောင်မှာနောက်နေ့သွားချင်လားဒီနေ့သွားချင်လား
နောက်နေ့သွားမယ်
နောက်နေ့သွား
နောက်နေ့ပေါင်းသွားလိုက်မယ်မနောက်နေ့ကဗီဒီယိုနှစ်ခုဆိုတော့နောက်နေ့မှပေါင်းလိုက်ပိုကောင်းတယ်
โอเคဟုတ်ပြီโอเคအဲ့ဒါနည်းနည်းများရဆိုနောက်နေ့ဆိုအဲ့ဒါဆို recording ဒီနေ့ဒီမှာပဲဆော့လိုက်မယ်နော် stop လုပ်လိုက်မယ်နော် sorry ပါlet's သွားပြီးတော့မဟုတ်တဲ့ဟာသွားနေပြီ okay stop sharing recording stop လုပ်လိုက်ပါမယ်